In this problem we're given four functions as equations, and we are to identify the domain of each, writing our answer in interval notation. When given one of our toolkit functions in this class as an equation, we tend to look for two situations for which, upon plugging in an input into the equation, the output is either undefined or is simply not a real number. These two situations would be any input value, in this case either x or t, that would lead to a fraction for which you're dividing by 0. It wouldn't matter what the numerator came out to be. It could be any number, as long as you'd be dividing by 0. Since division by 0 is not defined in mathematics, whatever the input value is that makes the denominator 0 would have to be excluded from the domain. So we would have a domain other than all real numbers. Looking at the equations, there's only one equation that has division as an operation, that would be this one. So G will have a domain other than all real numbers because there is an input value for which you'd be dividing by 0. The other situation, if ever, you're taking the square root of a negative number. With these four functions, you see that there's only one equation that involves taking the square root, and that's this one here. So for the function h, we will have to identify the input value x that makes the number under the radical a negative number. And it turns out there's many x values for which x plus 9 comes out to be negative, and we'll identify those and exclude those x values from the domain. Having said that, notice that with my first two examples, the function f, which turns out to be a quadratic function, and the function p, which is a linear function, is such that you would never be taking the square root, because there's no radical symbol in the equations, and you'd never be dividing by 0, because there's no division expressed in the equation. So it turns out that the domain of a linear function and the domain of a quadratic function is all real numbers. Think of it as you can plug in any input value you want. You'll always be able to square it and get a real number answer. You'll always be able to multiply that number by -9 and get another number in the real number system. And with any number, you could always add 3 and still get a valid result. So it turns out the domain of a quadratic is all real numbers, but since I'm writing that in interval notation, all real numbers means any number between -infinity and positive infinity. And then with interval notation, you have to decide whether to use a parenthesis or bracket, but you'll always see parentheses around infinity or -infinity because we never include those in our domain, simply because infinity and -infinity aren't real numbers. Or you could think of it as x will never actually take on a value of -infinity or infinity, because infinity actually is not a real number. It's not a valid input to any equation. For the same reason, a linear function always has a domain of -infinity to infinity, which just means that for any value of t in this case you provide me, I will always be able to take that number multiplied by 5 and remain in the real number system, and I'll always be able to take that result and add 8. Adding 8 to any real number in mathematics produces a result in the real number system. Now I'm going to turn to the example where we're given the equation for the function g. Remember, when we're given a toolkit function as an equation, the thing that we're looking for as far as identifying the domain is the following two situations. We're concerned about taking the square root of a negative number, as this would yield an output of the function that's not a real number. In this case, we have no radical symbol, so this situation simply would not occur. However, the other thing we are concerned about is division by 0. Any input value that would make this denominator 0 would have to be excluded from the domain. It turns out, since there's only one x value that needs to be excluded, and there's infinitely many inputs that we need to include, what's typically done is just identify the x values that we're going to exclude from the domain. We are going to exclude any input that would make the denominator 0. In this case, my denominator is x plus 1. So to determine the input x that makes the expression in the denominator 0, I simply copy the expression in the denominator down, write equals 0, and solve that equation. And then this process would work for more complicated expressions as well. If you were to subtract 1 on both sides, you'd see that when x is equal to -1, we would get -1 plus 1, or 0, in my denominator, and our output would be 1 divided by 0, which is undefined. So our domain is all real numbers except the one input that makes the denominator 0, which was -1. This is an acceptable way to express the domain. However, reading the directions of the problem, notice it states that we are to write our answer in interval notation. Sometimes it helps me explain how to write this in interval notation if I'm first allowed to sketch our solution set on a real number line. So here is a crude drawing of a real number line. We need to express all real numbers, which means I am to shade everything on the whole real number line except the one input value of -1. So the way this is typically done is you put an open circle on -1 to indicate that it's not included in the solution set, but all other numbers are included. Now, to write the answer in interval notation, we always start by writing the least number first. Since my solution set goes to the left forever to infinity in the negative direction, we call that negative infinity. We always put a parenthesis as to not include negative infinity in our domain, comma. Then going to the right, we're including all numbers up to but not including -1. So we'll put -1 and put a parenthesis indicating it's not included. So this interval represents this part of the solution set, but I haven't yet written an expression that includes this part of the solution set over here. So I must start at -1 again. That would be my least x value in this interval, but remember we are not to include the number -1, we're to exclude it, comma, and then all inputs count all the way to infinity in the positive direction. Infinity is actually never considered an input into an equation, so we put a parenthesis to indicate it's not included. Moreover, whenever a solution set has multiple intervals, in this case there's 2, we form a union between the two sets by using a capital U to represent a union symbol, indicating that our solution set is both inputs in this interval and inputs in this interval. Now let's turn our attention to the last example, the function h. So here's the function h defined as an equation, and with our toolkit functions, given a function represented as an equation, we always look for the following two situations. Will I ever be dividing by 0? Well, since there's no division taking place in our equation, this situation would never occur. However, since we do have a radical symbol, it is possible for some inputs that the expression under the radical, in my case x plus 9, may come out to be a negative number. This problem could be approached in two different ways. We could either approach the problem by finding inputs to include in the domain, or we could determine the inputs to exclude from the domain. It turns out in this case that there's infinitely many inputs to include, and there's infinitely many to exclude, so neither of these approaches is simpler than the other. However, it's typically approached by finding inputs that we are going to include in the domain, because that would give us the final answer to the question. So this approach involves identifying the radicand, which is always the expression under the radical. So for us, the radicand is x plus 9, and then we use the argument that the output of my function will be a real number whenever you're taking the square root of a positive, or if you were to take the square root of 0. So for any inputs that make the radicand positive or greater than 0, or it could be equal to 0. For those inputs that make that expression bigger than or equal to 0, we need to include the domain, because as long as that radicand's positive, the square root of a positive number will give a real valued output. And if x plus 9 were equal to 0, that's what this line represents, you would get the square root of 0, and the square root of 0 is defined to be 0, and since it's defined, the input that created that situation would be included in the domain. So the process in this situation usually involves writing down the radicand, setting it greater than or equal to 0, and then solving this inequality. To solve this inequality for x, I would subtract 9 on both sides, leaving only x on the left-hand side of the inequality. And since 0 subtract 9 is -9, I'd have -9 on the right side of the inequality. Because I'm subtracting, I will not switch the inequality symbol. In fact, you never switch the inequality symbol if you're simply adding or subtracting on both sides of the equation. But in case your radicand's more complicated, remember that if you ever multiply or divide by a negative number, in that situation, you would switch this inequality symbol to a less than or equal to symbol rather than the one we have now. So what I have now is a statement that says as long as your inputs are bigger than -9 or equal to -9, your radicand will come out to be either the square root of a positive number or the square root of 0. And whenever you take the square root of a positive number or the square root of 0, you're able to calculate that and get an answer that's a real number. So for such input that situation occurs, we include it in the domain. So this is our domain, however we need to write it in interval notation. I always find it helpful to draw a crude sketch of the real number line, and what we're trying to say is that we want to include the number -9, and we want to include all x values, all inputs, bigger than -9. So we're including all x values in the direction of positive infinity. So we will write the number -9, that's the least number in my interval. Since we want to include -9, because when x is -9, that creates the situation where we get the square root of 0, which is actually defined to be 0, which is a real number. And this is why we put a bracket indicating that -9 is included in our solution set. comma, then we put our greatest input value in the interval. Since we're including all numbers bigger than -9, this goes on forever towards the direction of positive infinity. So we write infinity. Since infinity is actually not a valid input to any equation, we put a parenthesis here to indicate that the infinity is actually not included as an input into the equation. As an interesting side note, since we were considering that the square root of a negative number would result in a number that's not in the real number system, if you wanted to find the domain by finding the inputs to exclude, we would exclude any inputs for which the radicand came out to be negative, meaning less than 0. Solving that inequality by subtracting the 9 over would state that we are to exclude all numbers less than -9. And notice this is the exact complement of our interval here, and this makes sense because if you are to exclude all inputs less than -9, that's the same thing as saying we are to include all inputs bigger than or equal to -9.